All right, class. So today we are going to start chapter 13, ethers, epoxides, thiols, and sulfides. So today we're going to talk about ethers and crown ethers today. That's what today's video lecture is going to be on. So let's just go over what an ether is. So an ether is a molecule where an oxygen is attached to two alkyl groups. Now don't get this confused with this molecule below here. Here, this oxygen is connected to an alkyl group on one side, and this isn't an alkyl group, this is an acyl group. So when you have an oxygen bound to an alkyl group and an acyl group, this is an ester, not an ether. So an ether is an oxygen bound to two alkyl groups. So not just two carbons, it's two carbons that are part of alkyl groups. Just like with all the other functionalities we've been talking about, ethers are prevalent in a lot of natural products, a lot of biologically relevant molecules. You see in vitamin E, there's an ether, a cyclic ether here. In fluoxetine, it's a powerful antidepressant known as Prozac. There's an acyclic ether here, and this is a chiral molecule, which is also interesting. And in morphine, which is important now because morphine is related to things like OxyContin and heroin, those epidemics. You see a cyclic ether here. So cyclic ethers and acyclic ethers are found throughout nature. So let's just go over the structures and the properties of ethers. So when you think about oxygen, the oxygen is sp3 hybridized. So its idealized bond angle would be 109.5 degrees. When you have water, this bond angle here between the two atoms is smaller because these electron pairs push these two bonds closer. As you start increasing the steric bulk of these groups here, you can see that the bond angle here starts to get wider due to steric hindrance. So when you go to methanol, the bond angle, the carbon-oxygen-hydrogen bond angle is 109. It's getting close to 109.5. And when you get to dimethyl ether, the carbon-oxygen-carbon bond angle is 112 degrees. And again, this is simply, so here the bond angle is less than ideal because these lone pairs are pushing these two bonds closer together, pushing this OH bond and this OH bond closer together. As you start making these groups bigger, the bond angle starts to increase. You also see that, and remember in alcohols we have hydrogen bonding that exists, so it's a dipole-dipole interaction, and it's the strongest of the dipole-dipole interactions. So when you have alcohols, they can act as both hydrogen bond donors and acceptors. Ethers, on the other hand, they take part in dipole-dipole interactions. Again, the oxygen's electronegative, partially positive, but there's no proton on the oxygen. So these molecules of ethers can only act as proton bond or H bond acceptors. So in alcohol, the electropositive proton on an alcohol can connect to or can bind to the partially negative oxygen on an ether, but no hydrogen bonding in ether. Because the ethers lack hydrogen bonding, what we find is that they have higher boiling points than alcohols, but because they are still polar molecules and they take part in this dipole-dipole interaction, they have higher boiling points than alkanes. So alkanes, by far, just the van der Waals interactions, the lowest boiling point. But dipole-dipole interactions, you can see the boiling point jumps quite a lot. Still though, this is a gas. And then once you start adding the hydrogen, if you just move the oxygen over and add the hydrogen bonding feature, all of a sudden you get ethanol with a really, really large boiling point, and you have a liquid that we now use, which is important for a lot of different reasons, but important now because it's the main component that you want to have in your hand sanitizers. And then in terms of when you're comparing different ethers, as the size of the ether increases and as the boiling point will also increase. Now, if I were to branch these molecules here, if I were to branch these alkyl groups, the branching would decrease the London dispersion force interactions, decreasing the boiling point. But if I'm just comparing a similar series of acyclic ethers, the bigger the acyclic ether, or the bigger the ether in general, the higher the boiling point. Now, ethers are commonly used as solvents because they're pretty unreactive, and also because they have low boiling points. Because they don't take part in the hydrogen bonding, they have really low boiling points and they're really easily removed. So these are pretty typical solvents that you might use in a lot of different organic reactions. So diethyl ether, tetrahydrofuran or THF, 1,4-dioxane. These are all common solvents that we would use in organic reactions. They have really low boiling points, so you can easily remove them, and they're very unreactive. Another advantage of using ethers, though, is the fact that ethers, because of this oxygen being partially negative, it can coordinate organometallic or metallic compounds. And that's useful because generally you would think about these compounds as not being soluble in most organic solvents. But because this oxygen can coordinate to this positive magnesium, this green reagent can be solvated by ethers. So acyclic ethers like diethyl ether, that's a common solvent used in the Grignard reaction. These are used mainly for all the reasons previously mentioned: their low boiling point, their unreactivity, but also for their solvation ability toward toward metal ions. We can even see this a little bit more clearly in what we call crown ethers. So a crown ether is simply a cyclic ether molecule where there are multiple kind of ethers in the molecule. And the way the naming works is the first number gives the number of atoms in the ring, and the second number gives the number of oxygens in the ring. And then you notice that the oxygens are kind of evenly spaced out. So 12 crown 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 4 oxygens. So these are interesting looking molecules, and you might be wondering, well, why do we even care about these molecules? Who would have made these molecules? What are these molecules even useful for? So remember, if you go back to this slide here, this acyclic ether is able to coordinate magnesium. Now imagine if these two ethers were connected together, right? And you had other oxygens on that cyclic on that ring, then you would get this crown ether. And crown ethers are interesting because they have this cavity in the middle. And if you look at this electron density map, because of the polarity of the ethers, the oxygen is partially negative, and you see that this middle cavity has a lot of partially negative character. So what that means is that these crown ethers, they can trap different cations, and depending on the size of the crown ether, that relates to the size of the cation that it can trap. So for example, 18 crown 6, this hole is the ideal size to trap the potassium ion because of this negatively charged pocket right here. This is really cool. This is, you can kind of imagine this kind of like ion channels in cells, right? And actually there's a whole class of antibiotics called polyether antibiotics that basically work by this feature of binding metals and then blocking up ion channels in different bacteria. So you can see that this crown, and the reason why this is important from a synthetic standpoint of being able to solubilize the metal ion is because, remember, we always talk about the metal ion as being a spectator ion, but it's still there. And if a metal ion isn't able to be solvated, then that whole ionic solid is not going to be able to be solvated in or solubilized in an organic solvent. So crown ethers can help ionic salts, crown ethers are used to help ionic salts needed for organic reactions to dissolve in organic solvents. So what does that mean? So potassium fluoride on its own is not soluble in benzene. But if I add the crown ether, what the crown ether does is, so what 18 crown 6 does is it will solubilize, it will coordinate the potassium ion. Then all of a sudden this crown ether is soluble in benzene, right? Because if you go back and you look at this electron density map, the outer portion of this is not very highly charged. It's going to kind of interact by van der Waals interaction, so it's going to dissolve in non-polar solvents. The inner part is where the metal is, right? So you're basically surrounding the metal ion with this kind of non-polar coat. And because the ion now has this kind of non-polar coat, you can dissolve it in a non-polar solvent like benzene. So KF can then be solubilized in benzene. And then you can do SN2 reactions with this fluoride anion. So again, depending on the size of the crown ether, that's going to dictate the size of the cation that you can coordinate. So 12 crown 4, that's for lithium. 15 crown 5, that solvates sodium. That coordinates sodium. 18 crown 6, that solvates potassium. So we just introduced, you just got introduced to ethers and crown ethers and the physical properties of them. Let me know if you have any questions. Thanks for listening and have a great day.